The law of conservation of energy. This law states that energy can't be created or destroyed, only transformed from one type to another. Think about that. Energy can't be created or destroyed. That means all the energy present today is the same as the amount of energy that was present yesterday. And it will be the same as the amount of energy present tomorrow. It can be transformed. That's the second part of this law. It can be transformed from one type to another. So where we think energy is actually being destroyed or created within a system, it's actually only coming from somewhere else or going somewhere else. It's only being transformed. So energy can't be created or destroyed, only transformed from one type to another. Transformed, that's important. It's these energy transformations that cause changes in the systems around us. If you think back to our definition of energy, which says that energy causes a change in a system, well, it's these transformations, energy transforming from one type to another, that causes these changes. Let's take a look at some examples. Up here, we have light energy or radiant energy. And during the process of photosynthesis, that radiant energy gets transformed into chemical energy of the food. And it is this transformation that causes a change in the carrot. It begins to grow and get bigger. And so you see that change in that system as a result of the energy transformation. Here we have electrical energy being converted into thermal energy. When you plug in your electrical stove, it's the electrical energy that heats up the burners, which then heats up the water and makes the water begin to boil, and that's a change in the system. So this energy transformation from electrical to thermal caused a change in the system. The water, it made the water begin to boil. When we eat food, there's chemical energy stored within the food, and when we eat that food, that chemical energy is transformed into mechanical energy, the energy of motion. And it's that energy transformation that allows us to do work. It's that energy transformation that allows us to move, so there's a change in our system. And our last example here is chemical energy from gasoline being transformed into the mechanical energy of a car. It might also be transforming into radiant energy of the headlights, or sound energy from the radio, or mechanical energy from the air that's blowing through the air conditioning system. So there's a lot of energy transformations that are happening from the transformation of the chemical energy in the gasoline to the mechanical energy and other types of energy in the car. So energy can't be created or destroyed. It can, however, be transformed from one form into another. Here is a diagram that illustrates this fact. We have this guy here, and he's pushing this tire up the side of the mountain. And as he's doing work on that tire, that work is being transformed into potential energy. And all the way at the top, all the work that he did as he pushed the tire up to the top of the hill was now being stored in this tire as potential energy. And as this tire just sits up here, that energy will continue to be stored as potential energy, and it won't really transform into anything. But once this tire begins to roll down the hill, that potential energy begins to transform into kinetic energy. And halfway down the hill, okay, we have both potential energy and kinetic energy. There's still half of the energy being stored as potential, since it's still halfway up the mountain, and half of the energy is being stored as kinetic, because half of the energy is now in the motion of the object. And as the tire continues to roll down, the amount of potential energy continues to decrease. The amount of kinetic energy continues to increase until we get all the way at the bottom of the hill, where all of the potential energy is converted into kinetic energy, and that completes the energy transformation. Another example of a kinetic and potential energy transformation is this roller coaster. Oh, he didn't go. Let's try to put that in slideshow view. Sorry guys, let's come back. There we go. Alright, so our roller coaster is going down the track, and look over here. We have kinetic energy potential energy, and this TME stands for total mechanical energy. And notice how the amount of kinetic energy and the amount of potential energy are changing throughout the course of the roller coaster, because the energy is constantly being transformed from one form, kinetic, into another form, potential. So what I want you to do, I want us to take a look at where the potential energy and where the kinetic energy is the greatest at different points along the roller coaster. So notice all the way up here, when the cart gets all the way to the top, right there, look at the bar. We have all potential energy. And as the roller coaster begins to go down the hill, that potential energy begins to get converted into kinetic energy. So the blue bar goes down and the orange bar begins to go up. And hold on, let's get it back to the start. So here it goes. There goes the PE's going down, KE's going up. At the bottom we have all KE, and then when it starts to go around the loop-de-loop, the KE turns into PE and vice versa. And so this energy transformation continues dependent upon the height of the cart and the speed of the cart. The higher the cart is, the more potential energy it's going to have. And the faster the cart is going, the more kinetic energy it's going to have. And the cart's going to always be faster as it's closer to the bottom of the roller coaster. But again, watch here, the total mechanical energy doesn't change, and that's the law of conservation of energy. No more energy is being created, no energy is being destroyed, the energy is simply being transformed from one form into another. All right, I don't like that view because it's a little small. So there we go. Now we can illustrate energy transformations on something called an energy chart. We like to call them LOL charts because we have our first graph here, our initial graph. It looks like an L, and then the O, the system, and then our final chart looks like an L. So we call them LOL charts, but they're really energy bar charts, and they illustrate energy transformations within a system. A system. Let's talk about that word real fast, because there's two different types of systems. There are closed systems, and if you look here to the left, when a door is closed, can you go in and out? Well, no, you can't. So neither can energy. Energy can't enter or leave a system if that system is closed. Here, the door is open, and when a door is open, can you go in and out? Well, sure, and so can energy. So energy can enter into a system that is open or leave a system that is open. And most systems that happen in nature are open systems. You only have a closed system really within a very confined laboratory environment. Otherwise, systems are naturally going to be open systems with energy having the freedom to go in and out. Now, I say energy can go in and out of a system, but there are only 4 ways that energy can go into or out of a system. The first way energy can go in or out is through heat. Heat is a result of friction. So if you have any kind of friction happening, then some energy is going to be leaving the system as a result of heat. Mass is a second way that energy can go into or out of a system, and mass can be solid, liquid, or gas. For example, when you eat a hamburger, that is solid mass going into your system. When you drink a soda, that's liquid mass going into your system. When you breathe in oxygen, that's gas going into your system. Solid, liquid, and gas can also exit the system, but I'm going to let you use your imagination on that one. Radiant energy is the third way that energy can go into or out of a system. And when we use the word radiant here, we're referring to both light going in or out of a system, like light going out of a light bulb or a glow stick or a firefly, or sound. Anytime sound goes into or out of a system, like right now I'm talking, and so sound is going out of my system, it's leaving my body, and it's exiting through the means of radiant energy here. And the last way energy can go into or out of a system is through work. And we saw that earlier with the guy who was pushing the tire up the hill. He was doing work on that tire, and that work was going into the tire as potential energy. So let's take a look at some example bar charts and try to identify them as being opened or closed, and why. So what would you say here? Do you think the system is open or closed? Well, I totally agree. It's an open system. Why did you pick open system? Yeah, I know. You're right. I heard you. Kidding, I didn't hear you. But I hope everyone said, because right here, you see this arrow leaving the system and it's labeled heat? Well, that's energy going out of the system through heat. And the only way energy can go out or into the system circle is if the system itself is open. So that's one way you can tell. A second way you can tell that the system is open is right here with this TE, the total energy. All right, so I have 1, 2, 3, 4, 5, 6 units of total energy, and I have 1, 2, 3, 4 units of total energy over here, which means energy was lost out of the system. How many units of energy left the system through heat? Well, if I started with 6 and I ended with 4, that means 2 units of energy left the system through heat. So there was a different amount of total energy, and you saw the arrow here going out of the system. So there's 2 ways to tell that it was open. How about this one? Is this system open or closed? Yep, it's closed. Why? Why did you say it was closed? That's right. The total energy is the same. 1, 2, 3, 4 bars of total energy to begin with. 1, 2, 3, 4 bars of total energy to end with. So no energy came into or left the system. I can also see that right here. I don't see any arrows going in or any arrows going out. So this is a closed system. So one of the things you guys need to be able to do is look at an LOL chart and identify it as being open or closed. And remember, there's 2 ways to do that. First way, look at the system. Do you see any arrows going in or out? If you see some there, then it's open. If you don't see any, then it's closed. The second way is to look at the TE, the total energy. You have the same number of units at the beginning as you do at the end, and then you know it was a closed system. All right, let's try to make your own. Here's a blank bar chart, and the situation I want you to think about is a girl doing a yo-yo. Okay, right now the yo-yo is in a position where it is going up, but it's not all the way up. She's yanked on it, and so the yo-yo is beginning its upward descent back up into her hand. I want you to determine how many units of potential energy do you think there are? How many units of kinetic energy do you think there are? Add those together to get your total energy. Is there anything going into or out of the system? And show me that with arrows. And then when the yo-yo gets all the way back up into her hand, what kind of energy would be present at that time? How many units of potential? How many units of kinetic? Add those together to get your total energy units. How many units do you start with? It doesn't really matter, 5 or 6. Just be realistic. Don't give her like 25 and draw, 25 little boxes right there. That's just silly. Just, use anywhere between like 0 and 10 units. Okay, so I want you to pause, draw this LOL chart, and fill it out, and then come back to me, and I will show you what I came up with, and then we can compare that with what you came up with. All right, pause now. All right, now that you have had a chance to make your LOL chart, I started with 2 units of PE, potential energy, because she's off the ground, but not off the ground a whole lot, so I just gave her 2. I gave her 4 units of kinetic energy because it's closer to the ground, and like we saw with the roller coaster, the closer to the ground something has, the more kinetic energy it has. So I gave her 4 units of kinetic energy, and I add those units up to get 6 units of total energy. All right, let's think about what might be going into or out of the system. She has just pulled this yo-yo. That's work, all right? That's work going into the system. So I say that's 2 units of work going into the system. There's also going to be some friction between the string and the yo-yo itself, so I say that's maybe a unit of heat going out. That's going to result for me in, let's see, 1, 2, 3, 4, 5 units of potential energy, because then the yo-yo is going to be all the way at the top. A couple units of kinetic energy. I add those together, 1, 2, 3, 4, 5, 6, 7. 7 total units. I started with 1, 2, 3, 4, 5, 6. All right, 2 went in. That's 8. 1 went out. That's 7. 1, 2, 3, 4, 5, 6, 7 units of energy. So we just illustrated an energy transformation and the law of conservation of energy, because energy wasn't created or destroyed. It was only changed forms. That's it for today, guys. I'm out.